So, last day of notes ever. So what we're doing is we are trying to draw conclusions from your experiment that we have conducted. So we are trying to answer this question of, is the difference I see significant? So what we're doing is we're taking a whole bunch of scenarios and you're trying to figure out if what the results were actually because of the treatment, meaning what you were trying to figure out, whether it was like something about sleep versus no sleep, or food versus no food, whatever it is you're trying to figure out. Did the results happen because of that treatment, or did it happen purely because it was by chance and it just would have happened anyways regardless of what you did? So when you're comparing two treatments, it's important to assess whether the observed difference is real because of the treatment, or if it happens to be just random assignment into groups. So could the difference you see be due to the random assignment, or is it a real difference, which is also known as an unusual difference, or a statistically significant difference? So to help you think about this, if we look at this, we randomly assign everyone into two groups. One group walks together every single morning, whereas the other group does not. So then the walking group at the end of the little study ends up doing better on a fitness test. So what you would be trying to figure out is, did that group do better because they were all walking together in the morning? Or did they do better purely because you happened to put students who were more fit in that group versus the group that didn't walk every single day? So you're trying to figure out, is the result actually because of the walking they did, or is it a result just because of random assignments that you put into group? You put students who are more fit into the group versus the other group. So that's what you're trying to figure out here. So one thing I wanted to go over quickly is some vocab with you, so that when I say these words, hopefully you remember what they mean. So we have a new dog food, which is specially designed for older dogs, has been developed. A veterinarian wants to test this new food against another dog food currently on the market to see if it improves dogs' health. So 30 older dogs were randomly selected and randomly assigned to either the new food group or the current food group. After they were fed the new or current food for 6 months, their improvement in health was then rated to see which one did better. So the experiment that's actually happening here, what is our experiment? Does anybody think they know? Yep, so they assigned two groups of dogs, one with the new food, one with current food. So assigned two groups of dogs. New versus current food. To see if their health improves. So that's the actual experiment that's being done. So what would be our subjects within this experiment? Older dogs. Which again, I feel like that needs to be even more specific, because I mean, if you're looking at like the little yippy dogs that live for like 20 years, what constitutes them as being older versus like a Great Dane that only lives for like 6 to 8 years or something like that. So, yeah. Bigger dogs don't live as long as the little ones do, sadly. So our response variable. What our response variable is kind of like, you want to think of your outcome. So our response variable here would be the dog's health. What you're looking at the end, that's your outcome of the experiment at the end, is what is the dog's health. So our treatments, what would our two groups be getting? So new food would be one of the treatments that's being given. The other one is their current food. So then our random assignment, that means that dogs are randomly assigned into the two groups. And then that one sometimes gets confused with the random selection, which would just be that dogs were randomly selected to participate in the experiment. And then our last two down here tend to get a little confusing. We have induced variability and natural variability. So your induced variability would be that the new food improves the dog's health. So your induced variability is pretty much your treatment that you're trying to test. In this case, they were testing the new dog food, actually works and does what you want it to do, which is improve their health. Whereas the natural variability, that would be, they like to use the phrase by chance for here. Or really in this scenario, it's more of the dog's health improved regardless of the food that they had. So their health improvement was natural. It didn't get altered by the treatments, is one way to look at it. Now, they're not going to always ask you to sit here and write out what each of these are within an experiment, but you never know, it could show up, and they could ask like a multiple choice question of, in this scenario, which one is the response variable? Or within this scenario, which one is the induced variability? So you got to make sure you know what those words mean. All right. Let's take a look at our first example. So we're taking a look here at the study. They're looking at lack of sleep. The question that they had were, researchers in a sleep lab at a college decided to see how a night of no sleep affected the ability of students to answer 50 addition problems in 1 minute. So they took 30 volunteers. They randomly assigned those 30 volunteers into two groups. One group was not allowed to sleep. The other group was allowed to sleep. And then they came in the next day and they had to answer 50 addition problems in 1 minute. So these are the results. So group one, who had no sleep, these were the number of questions they got right, or they answered out of the 50, I should say. And then group two, this is the number of questions that they answered out of the 50 in the 1 minute. So first thing to try to analyze our data, they want us to find the mean of each group. So I want you to go find the mean for group one, and then find your mean for group two. So by looking at those two averages, our 26.3 and our 32.6, does it appear as though getting sleep helps in answering addition problems? Well, the people with no sleep got that score versus the people who got sleep. Does it look like it helps? Yeah. So yes, it appears as though sleep helps. So then B wants to know, is it true that a person who gets sleep will always answer more addition problems than a person who has not gotten any sleep? Support your answer from the experimental results. No. Why would it be no? Well, that doesn't go with the experimental results. Didn't those guys who got no sleep do better than those guys who did get sleep? So, does a person who gets sleep always answer more problems? No. Some people with no sleep did better than some who got sleep. So it was not always true. There were some instances where it was not true. So what we have to do now is we have to figure out what we refer to as the observed difference. So based on our means up there, they want to figure out what the observed difference is. So you would just subtract group 2 minus your group 1. And what do we get? I got 6.3. 26.3. Yes. So now the nice thing is when you go to figure out your observed difference, they will always tell you what order to subtract it in. They're not going to like sit there and make you try to guess. They will actually always give you that. So that's a nice thing that they help you out with there. Bless you. So then they want to figure out, is this observed difference of 6.3, is that due to chance, or is that really because sleep helps you add? Does sleep actually help you add numbers together? No. So whether it's due to chance or if it really helps, we don't know. I mean, in group 2, you could have just had some really smart people, like a whole bunch of Sheldon Coopers in there. There could be a whole bunch of Mrs. Pelkeys in that group before she got pregnant and actually had a brain. So in order to be able to answer that question, what ends up happening is they then take those 30 people and they just reorganize them again and they create 2 new groups. But this time when they create the new groups, they don't care whether they got sleep or no sleep. So in group 1, you're going to now have a combination of people who get sleep and don't get sleep. And in group 2, you're going to have a combination of people who get sleep and who don't get sleep. So a simulation will take our 2 groups of data and randomly scramble them up into 2 new groups. And it will do this over and over again for 100 times and calculate the difference of the means like we did up above. So they calculate the observed difference over and over and over again. So all these dots represent all the different observed differences that they calculated when they just re-scrambled the groups up 100 times and found the difference of their means. So again, what this does is it takes the 30 people and regroups them. So again, in those groups, you have some with sleep, no sleep, some that have sleep and no sleep in the other group too. So regroups them. It then averages their results, just like we averaged their results up above, but once they're regrouped, it just finds the average of that new group. So it then compares the new groups. So then what ends up happening is if you have 2 groups that are a combination of the people who have sleep and who don't have sleep, should there be a difference in their numbers? No, because you have a combination of the people who got the treatment of sleeping and then the people who didn't get any sleep. So when you scramble them all up together, there really should not be a difference between the averages of those groups. So when mixing groups, you would expect there to be no difference in the means. So if there was no difference in the means, that means all of those dots should be up there on that line at 0. But they're not. So why do you think they're not all on that line there? Well, if we take a look at our numbers up here, what if in one of the groups was all these people, and then all those other people were in the other group? What's going to happen to that score? It's going to be a big, huge difference, because the average of these people versus the average of that people is going to be significantly higher. So the randomization of the groups can also have that kind of an effect on it. So that's why it creates all these different dots here. So now I have little arrows here to go over what these means. So a -4 here, that means that the average for group 2 was 4 points lower than the average for group 1. Because that would be, you took group 2, subtracted group 1, so the average for group 2 was lower. So if we had a negative number here, we could say that either group 2 didn't do as well as group 1, or we could even flip it and say group 1 did better than group 2 did because it was negative. So then our +4 over here means that the average for group 2 was 4 points higher than group 1. So to figure out whether there's actually a statistical significant difference here, what we have to do is we have to figure out percentage-wise, where does our observed difference from the actual experiment itself, so our 6.3, we have to figure out where that would fall based on the simulated data from when they randomly grouped everybody together. So our 6.3, I would say, falls approximately here. So you always want to take that score that you have and everything higher than it if you're positive. So since we were positive 6.3, I'm going to do 6.3 or higher. How many dots do we have total there? 5. And they did this 100 times, so this would be 5 out of 100. What would our percent be there? 5%. So that means our 6.3 or higher shows up 5% of the times out of all of the different simulations that they ran here. So what that tells us then, interpreting that 5%, can we confidently conclude that the difference in the sample means is due to the treatment or due to natural variability? Support your argument using the distribution above. So since it occurred only 5% of the time, we call that an unusual value. So since it's unusual, because it only happened 5% of the times, that makes it statistically significant. So since it's unusual, that makes our results statistically significant. Which really, that's what you want to have happen. You want it to be statistically significant. So then we can finally say at the end, therefore, we can say it's a result of the treatment and not by chance. So when you're trying to write these explanations and interpreting your results, words like unlikely, unusual, possible, those kinds of words are words that you want to use in there. We did say that was unusual value, so we did use one of those words. So to figure out, this is kind of like our rule here. If the observed difference from an experiment is extreme and not typical of chance behavior, it may be considered statistically significant and possibly not the result of chance behavior, but due in fact to treatment. So our extreme would be 5% or less. So if you go and you calculate how often or how much does this occur, and it's 5% of the time or less, that's statistically significant. It's an unusual value because it's only 5% of the time. And that's what this is saying here. That's our rule of thumb. Less than 5% chance that it happened, then you can say it's because of the treatment. All right, let's try a few more examples.
They all that long?
Huh?
They all that long?
No. All right, so our next example here, trying to figure out if there actually is a home court advantage for the SU men's basketball team. No, somebody made this up. So here we are. We have the overall record was 18-13. That's wins to losses. If you guys don't know how they normally write it. So at home, they had 13 wins and 5 losses. Away, they had 4 wins and 7 losses. So this time, instead of finding the averages like we did for the last problem, you can't really find the averages of like the scores at each game. So there was really no average we could find here. So we're going to do proportion here. What proportion of home games did they win? So they won 13 games out of the 18 played at home. So let's have you figure out that as a decimal to the nearest thousandth. So the proportion of their wins at home is 0.722. So then their proportion of wins away would be 4 out of 11, which would be what? Point what? So then they want to know what is the observed difference in proportions of successes in this sample. So they want you to figure out home minus the away. So 0.722 minus 0.363. What is our observed difference? .359. So then again, we want to know, is that number statistically significant or not? So if the team is equally likely to win at home versus away, what difference in the proportions would you expect to see? So if they're as equally as likely to win at home as they are away, should there really be any difference in their scores? No, they should win just as many at home as they do away. So I would expect to see none. So then I went through and I simulated for 100 seasons, each with 31 games, wins versus losses being as equally likely to happen. And then I split it into home versus away and found the difference of their proportions like we did up above. And it gave me this little chart here. So we have to figure out, is the Syracuse men's basketball team's performance from 2014-15 at home statistically significant? Explain your answer. So we got it to be 0.359, which I would say is approximately there. So we got to count how many dots we have at 0.359 and higher. Well, count on your paper then. Count on your paper then. It should be. Oh. There should be 9 dots, and it's out of 100, because remember I just said I did it here up out of 100 seasons. So what is our percentage? 9%. So now 9%, that still is a pretty low percentage. So this is still pretty rare to happen, but it does not fall within our 5% that we say is our cutoff. So it's not statistically significant. So it's pretty rare. But not statistically significant. So would this be actually a home court advantage, or would their wins just be by chance? By chance. Because it's not statistically significant, their wins are by chance. So really that's their cutoff that we give you. 5% or less. That means it's significance, the treatment actually did it. All right, let's take a look at our last example. We got bamboo here. Bamboo is becoming increasingly popular in home construction because it is very fast growing. The yearly growth of one bamboo was studied under 2 conditions. So we have 100 plants grown indoors and 100 plants grown outdoors. Did you guys know that they actually tried to use bamboo at Pine Grove? They put it on the floors, and then they had to replace the floors. Because bamboo was so soft, they would put like filing cabinets down and they would sink into the floor. And then you try to move the filing cabinet, and now you've got this crease, like print of the filing cabinet down there. And I guess even like some of the women's high heel shoes were like going into the bamboo floors. So they had to redo the floors.
So they opened the school with the bamboo floors and had to replace them.
I don't remember if it was the entire school, but I think a good portion of the school. They had the bamboo flooring.
Oh, so they had to put them in the school, then move them.
All right. So here, they've already calculated your means for you. They took the mean of the heights of all 100 plants grown on the outdoors, and then all of the ones grown on the indoors. So they want us to determine the mean difference, outdoor minus indoor, and explain what this number means in context of the problem. So let's have you go ahead and figure it out first. What is your difference? And then we'll see if you can explain. So you should get negative 10.3 when you subtract them. Now there's 2 ways that you could write the explanation for this number. You could say the outdoor group on average grew 10.3 inches less than the indoor group did. Or you could flip-flop it and say the indoor group on average grew 10.3 inches more than the outdoor group did. Whichever way you want to phrase it, you can. So after I calculated that number, again, trying to figure out if that is a significant number or not. So I kept taking all of the trees, breaking them up into two groups. I had some indoor, outdoor trees in both groups. And I ran 2,930 simulations. So did that 2,930 times. And it created our distribution there. So using the information provided, determine if the observed mean difference was of statistical significance. So our negative 10.3 would fall approximately in there. Now this time, all of our other problems have been positive differences. This one's a negative difference. So instead of going to the ones higher than it, you're going to go for the numbers lower than it. So you're always going to go towards the outside that's closest to it, depending on what your number is. So this one's negative, we're going to go lower. So now we have to figure out what number does this bar right here represent. So these are going up by hundreds, so what do you think that this little group here approximately represents? 30, yeah. I said like 25, 30, somewhere in there. So again, this was out of our 2,930 simulations that I ran. So let's figure out our percentage. So 25 divided by 2,930 times 100. I got like 0.853 is what I got with my 25. Because when you divide, you should add 0.00853. So would this be statistical significance? Is this an unusual value? Is it less than 5%? Yes. So this is an unusual value. So it is statistically significant. So what can we say about growing the bamboo trees indoors versus outdoors? Growing the trees indoor had a positive effect because they were on average, they were taller. Based on our distribution there of the differences, they were taller.